intro activity, really because this is going to go through small bases, large bases, as well as the Zaitsev versus Hoffman product. That vocabulary you're going to hear us use a lot as we go through elimination reactions. So when it comes to E2 reactions, so this really only pertains to E2 reactions, small base versus a large base could give us different regioselectivity. So it could give us a more substituted versus less substituted alkene. When we talk about small base, we're talking about a single atom, methyl, primary, nothing big, right? So you have this O minus that has one carbon connected and then a methyl group after, or you have this N with a negative formal charge with only a methyl, versus a large base where you're looking more at your tertiary connectivity, secondary, or then it's connected to a secondary or a tertiary carbon. So you notice you have this carbon connected to three others, which is also, right, this is an ethyl group. So it just becomes large, right, bulkier. We're going to focus specifically on a couple bulky bases that we'll talk about. But the difference between the small base and the large base is whether you create the Zaitsev product, which is the more substituted alkene, or the Hoffman product. So the difference, Zaitsev is the most substituted alkene, Hoffman product is the least substituted alkene. Regioselectivity will matter based on whether the base is small or large. Now again, this is relevant only for E2 reactions. So for those reactions that happen all at once in a single step. Now, when it comes to the different reactions, all E1 reactions, so E1 reactions form the carbocation and then form the double bond. All E1 reactions will always follow Zaitsev's rule. So E1 reactions will always produce the most substituted alkene. E2 reactions, if a small base is used, it will obey Zaitsev's rule. So if a small base is used, it will form the more substituted alkene. If a large base is used, we would see a Hoffman product. So we would actually see a less substituted alkene as the major product, and that's because of steric hindrance. So a steric hindrance, a large base, is required to pull off the least hindered beta hydrogen. So when it pulls off the least hindered beta hydrogen, that's going to create the least substituted alkene product. So when it comes to looking at E1 versus E2, here are recap slides with all the information on E1, all the information on E2, kind of like we did for SN1 and SN2. So with the E1, kind of come over here for the recap of the E1 reactions. So E1 happens in two steps. The one means that it's a unimolecular rate determining step, which means you have to have multiple steps for that alkene to be produced. So a carbocation is formed. Because a carbocation is formed, we have to pay attention to the stability of the carbocation. Tertiary, secondary carbocations will work. Primary will be iffy. Methyl probably won't work. You'll notice here, though, it says it will not work with primary carbons, only because even if you try, or you try to make it work, kinetics has shown that it's not going to actually go through the E1 process, which means if you have a primary carbon, we're going to shift over to the other type of reaction. A strong or weak base can work with E1 because the carbocation forms first, but usually we are going to see a weak base used. Weak bases tend to be neutral, so ethanol, methanol, those are weak bases. And then polar protic solvents favor E1. That's because it stabilizes the carbocation. So methanol, ethanol, not only are those neutral nucleophiles, weak bases, they're also protic solvents. They can hydrogen bond. And then E1 reactions will always form the Zaitsev product, more substituted alkene. Then we shift over to the E2 reaction. So these are the one-step reactions. No carbocation is formed. And so this is going to work best with less steric hindrance. Methyl being the fastest, then primary, then secondary. It still might occur with tertiary alpha carbons, but you're going to need a very strong base, small, strong base, to try to get it to work. If we see a tertiary alpha carbon, that's typically going to go over to the other side, depending on the solvent. So we do need a strong base. Strong bases we see with negative charges. So at the bottom, I showed the small base versus large base, and notice how the small bases with these strength all have negatives. This came out of the intro activity. We have all these negative, OH minus, NH2 minus, OCH3 minus. Those are your strong bases. But then with E2 reactions, we can control the regioselectivity. Regioselectivity is, are you forming the more substituted alkene or the less substituted alkene? And to control regioselectivity, that's based on the size of the base. Small bases will produce the more substituted alkene because there's less steric hindrance. The bulky bases, or the SNN is strong non-nucleophilic bases, those will form the Hoffman product. That's the less substituted. Because again, due to steric hindrance and the size of those bases, it's going to pull off the least hindered beta hydrogen. And so a lot of times when we see these bulky bases, this is where we have to keep in mind that the less substituted alkene could form. This is only for E2. E1 always produces the most substituted alkene. And then the small, strong base will also follow Zaitsev's rule. So just looking at a recap of the mechanisms themselves. So E1, because it happens over multiple steps, we have our leaving group leave, very similar to what SN1 looked like. Then we just have to remember that elimination is about removing beta hydrogens. So we have to focus on where's our alpha carbon, where are our beta carbons, and then where are our beta hydrogens, and then how will the base remove the beta hydrogens. So for this example, we have the oxygen attacking, right? It's going to remove that H, and then the bonding electrons are actually going to form that double bond. So then we have an elimination product. For E2, we have lots of arrows because it's a single mechanism. So for E2 reactions, we have lots of arrows within our mechanism to get from our starting alkyl halide to our final alkene product. So our strong base attacks the hydrogen, then bonding electrons form the double bond. Double bond is formed and the leaving group leaves. That happens all at once. That's a concerted mechanism. So it just shows the recap of each of those mechanisms, E1 versus E2. And then I put everything kind of on one slide here. We looked at the strength and different examples of bases up here. We looked at this yesterday. Just looking at how strong bases tend to come in one of these forms. So these all represent strong bases. And then also down here showing the bulky bases. So just giving you some examples of things that we see. Potassium tert butoxide is one. Remember the K+. If I remove the K+, now you have that O with the negative charge. There is your strong bulky base. All right, LDA, again, lithium is just that cation that's used to bring in the anion. So you have that N with a negative charge. There's your strong base. And then triethylamine. Triethylamine, here's a bulky base. So you have ethyl groups, 3 ethyl groups off the nitrogen, and then you have that lone pair. So that's another bulky base. So the bulky bases are ones that just have lots of steric hindrance. It's going to be a lot harder for them to attack and remove a beta hydrogen.